All right, let's get started. So you guys already received my email, right? Just make sure. Did you? Like last week? The week before last week? Yeah. I sent out the lecture. Yeah. So today I'm going to talk about the problems in worksheet. And then there are two problems, right? And then I'll talk about the second problem first, because I think that problem is most important. And then I'll talk about the first one afterward. All right, I will start from the motivation as well. So basically, I think the second problem is all about the Master theorem, right? And then why we need to learn Master theorem. That's the motivation. So we learn how to solve the problem recursively, right? So for example, this series you learn from the class, and then basically that's the recursion step we need to have, right? For n, we can decompose the original problem into n minus 1, n minus 2, right? And then for the problem you face in the homework one, you basically decompose the original problem into 3 subproblems, right? n minus 1, n minus 2, n minus 3. Yeah. And then for the times x times y this problem, we also use the recursion, right? We call this divide and conquer. So why we need to use recursion? Yeah.
So if a problem can be disintegrated into sub-problems, wherein the solution of that sub-problem is same for its further sub-problem and for its parent problem, that's when we can use recursion and change the input on which the part would be working. So yeah, basically solving of sub-problems which has same solution.
Yeah. But why we need to solve the subproblems instead of the original problem? Yeah.
Because the sub-problems have a smaller size than doing the original problem multiple times.
Yeah, that's correct. So let's look at those time complexity first. So for this time complexity, we know it's going to be exponential, right? Probably around like roughly around like this, right? And then for this problem, it's also exponential, right? Probably around like this, right? And then for this problem, it's going to be polynomial, right? We learned that from class. That's going to be like this, like n to the power of 2.
Where does that 0.6 come into picture? Like,
oh, this one, you can do the approximation. It's going to be 0.6. You can prove that from like induction step. Like, yeah, if this is going to be larger than this, you can check out the initial step and then do the inductive step. Yeah. So you see, like those recursion grow exponentially. So we don't really like that, right? But for this one, it's polynomial. So it's like that's the thing we want, right? But unfortunately, this is like as fast as the original problem. So we further like improve that from 4 to 3. And then we can have like a lower time complexity. Yeah.
One thing I'm so confused on, especially with the example we gave in the lecture, was like when we're like even like talking about something like say the multiplication or like some other thing we have to solve, like what exactly makes like the steps to use like a sub-problem as opposed to just steps? You get what I mean? Like what is like a sub-problem within like the context of an actual problem?
For example, like for this multiplication, we don't need to multiply the original 2 array or 2 string, right? We just need to multiply the like half of that.
Yeah.
And then do that 4 times. And then for the original problem, we still need to have like an ON time complexity. But other than that, we can just move from the original problem to the subproblems.
Oh, so we're just doing the same operation for like each like branching factor for each like level.
Yes. So for this level, for the original level, we still need to do like ON, but other than that, we can solve the remaining part for this by solving these subproblems. Does that make sense?
Somewhat.
Okay, yeah, I can give you the concrete example later. But basically what I'm saying is that the reason we want to use recursion is we want to reduce the complexity, right? But sometimes it works, sometimes it doesn't, right? You see the exponential and polynomial examples. So anyone has any idea why those are exponential and this is like polynomial? No? Oh,
Is it because the T of n is getting divided by 2 instead of like subtracted?
yeah, correct. So basically we make the subproblem. So the subproblem is smaller than the original one, right? But there's no like big difference, right? Just the difference is only one, a constant. And for this it's the same. So basically they are roughly the same. So we are actually increasing the problems for those two recursion, right? But for this one, we actually make the subproblem much smaller, right? But that's not enough, right? Because for this case, it's just the same as before. And then we want to make it like 3. If we go from 4 to 3, the original problem can be solved by much lower time period. Does that make sense? Yeah. Okay. So let's look at the theorem first. So that's the basically that's the formula you can follow. That's the inequality, and then those are the conditions. These are the result. And then before explaining this part, I will go through the let me think. Okay, let me just erase this part. Okay, so that's the formula we have, right? And then so what does that's the result. And then right now what I'm doing is going to convince you guys this actually can be expressed by this way. Okay, so let's look at the formula first. So what does this mean? This means that for the original problem, we just need to spend this time. And then other than that, we can reduce our problem or decompose our problem by solving this, the subproblems, right? The subproblem, the size of subproblem is going to be smaller because B is going to be positive, right? So for the let's look at the work on each layer first. So for the original layer, or like the top layer, or like the root. What's the complexity we still have? Time complexity. That's going to be this, right? Yeah.
So like what is A, B, N, and D represent?
They're the constant, and then it really depends on how we formulate the problem. For example, the times problem, this A is equal to 4, and then this is 2, and this is 1.
So the A is the branching factor?
Yes, A is the branching factors, and then that's the size of subproblem, each subproblem, and then that's the time complexity we are going to solve for each layers.
Oh, okay, so the D is like the number of subproblems per layer.
You mean B?
No,
B?
B, like
No,
numbers.
B is the, because you cannot just, sometimes you can directly transfer your original problem to some problems,
Mhm.
but sometimes you cannot. You still have to do something, right? You
Oh,
probably need to do some like comparison or some calculation. That's the complexity for that.
okay.
You know, for example, for the x times y, this question, eventually when you solve the some problem, you still need to add them together, right?
Okay, so
So
then,
that's the time complexity for that operate.
okay, so then N is the number of subproblems per layer. Or what does N represent?
And n is the input size.
Input size, okay.
Yeah, so the input size, and then A is the branching factors. That's the input size for sub problems, and then that's the time complexity for calculating the problem in each layer. So for the root, we still have this time complexity, right? How about the second layer? Or like the first layer? This is like k equals to 0, and this is like k is equal to 1. How about when k is equal to 1? We will have like this input size, right? So that's going to be like this. Does that make sense? But we don't only have one. We have how many? 8. Right? So for the next layer, each subproblem is going to be divided again, right? That's going to be b to the power of 2. So, and then we have more subproblems in the second layer, right? So that's going to be n squared . Oops, I forgot. Does that make sense? Would be this. Originally, we have n, and then we have like n over b. So that's the input size. And then we know that we need to solve that by the power of d, right? And then that's what happened in the first layer, and then the second layer, we have this, right? Does that make sense? Okay, so eventually we have something like A. Make sense? Yeah.
So why do A and B get raised to K but not N?
A doesn't, right? Oh, you mean raised to K?
Yeah, why not N? Like why only A and B?
Yeah, because you see like first layer, we have 8 problems. The second layer, we have n to the power of 2, right? And then for each subproblem, that gets smaller over time.
Yeah, so why don't we square N?
Square n like this?
Yeah,
You mean like K?
yes.
Because this is the original size, right?
Oh, okay, so it stays at the original size.
Yeah, the original size, and then over the layers, that becomes smaller. So that's the reason we are going to divide n by b. Does that make sense? Yeah, okay. So yeah, that's the work we are going to have for each layer, right? Does that make sense?
Yeah.
Okay, so at the end, how many layers we have? Or what's the depth of this problem? Make sense? Because each time we are going to divide the original problem by the factor b. So eventually, that's the number of layers we have, right? So if we plug in this k into here, you see what is if you plug in k to here, what is b log en? That's basically n, right? Okay, So that's n. And then, so basically the last layer is going to be, this is n, so canceled out. B doesn't really matter, right? This part doesn't really matter. And then you plug in this part into K here, and then you'll get the Does that make sense? Because you can swap those two, right? Yeah,
So why does B not matter?
because when you plug in K here,
Mhm.
this part is going to be n,
Oh, okay.
And then
So
you
never
cancel
mind,
out.
I get it.
right? And then so, but if you're plugging K to here, you still have this term, right?
Got it.
Okay, make sense? So you see that originally we have this amount, right? Like this amount of work. And then probably you will increase, probably you will reduce. We don't know the number of subproblems. Probably you will increase, probably will reduce. We don't know, but eventually we have this amount. So you can imagine, in the first layer you're going to solve this, and then the second layer you're going to solve this, and then you'll solve this, and then you'll solve this, and then you plus all of them together. Right? Make sense? And then what's the total time complexity? So if you look at this first, and then look at this inequality, that totally makes sense. Why? Because what you see, like those are polynomial, right? So what we need to compare is here. Who is larger? Right?
Yeah, so who dominates, right?
Yeah. If D is larger than this one, which means that the problem is getting smaller over theirs. And then eventually you don't really care about the subproblems, right? You just need to care about how to solve the original problem, original input. So that's going to be this case, right? If D is going to be larger than this, which means that the subproblem is smaller over time. So the time complexity is going to be this. And then if they are equal, means that you actually need to pay attention on whole problems, right? So the total time complexity is going to be n to the power of d, n to the power of d, n to the power of d, n to the power of d. How many? This amount, right? Because we have that many layers. Make sense? So the time complexity is going to be this, right? Like each layer we are going to solve this. We are spend this time to solve, and then we have those layers. Because we cannot ignore the others. They are equally important, right? So that's the reason we have to sum up all of them. That's the time complexity. And then how about if this is larger than original one? We don't really care about the root anymore, right? Because we can just pay attention on these. And then we just need to really focus that because this one is going to dominate the whole thing. Does that make sense? Any question? No question. Okay, yeah.
So in that original in that original formulation, A T n over B, we don't even need to calculate that, right? If O dominates, if O and
We still need to.
Okay.
We still need to, but when we do the analysis for the complexity of the algorithm, we just ignore that part.
Yeah.
Right. So
Okay.
you still need to, for your algorithm, you still need to calculate
Okay.
that. But when we do the complexity analysis, we don't need to care about the rest of the part.
Got it.
Yeah. So let me just stress one more time. So this means that root is going to dominate, right? So we only need to pay attention to the complexity in the root. And then for this part means like eventually the leaves, the time complexity is going to be same as the leaf, and then all of the layers, they are going to be the same. So in that case, we need to calculate all of the layers. Also, when we do the analysis, we need to sum up all the complexity. So that's going to be each layer and then how many layers we have. right? And then for this case, this is going to dominate the time complexity. So we don't really care about what happened before. We just need to know how many leaves we have, right? So that's the for this case. So let's look up the example, and then oh, by the way, not sure if I have time, but let me just quickly write this down. So the professor used this several times, right? Like when you have this geometric series, and then you can have this kind of time complexity. Basically, it tells the same thing as this logic. I just didn't use this mathematically, but they tell the same thing. Why? Okay, so let's look at this. You basically do the summation for all of the C, right? And then if C is smaller than 1, which means like when you the later term is going to be much smaller. So eventually you don't really care about that. You just care about the first term, right? The first term is going to be something to the power of 0. That's going to be 1. So that's the reason we have constant time. And then for this one, each term is going to be the same. So you have how many? And so that's the reason, right? And then for this term, it's going to grow, right? So that's the reason you care about the final, the latest term. That's going to be like this. Does that make sense? It's the same thing here. When you have the summation, if that's not infinite, you can do the logic in your mind like that. Yeah.
So why is that last one not in big O form as opposed to the others?
They actually all have, right? But this is like big O, oh, big O. Yeah, big O.
Okay, got it.
Yeah, big O, and then the first term. Yeah, and then any term, and then the final term, like that. So the same thing. Okay, let's take a look at the example. So for example, the first example is going to be like this, right? So what happened in the first layer? Or like the root cause? If we want to solve this problem, what's the size of work we are going to have? Let me just use like W0. 0 means the first layer. So what's the size of work we're going to have? That's going to be in the first layer. So we will have something for some problems, right? But later, right? So for the first layer, we're going to, for like 0 layer, we have this. Make sense? And then what's the size of work for the following?
42n over 2.
40.
2n over 2.
Yeah, that's right. So we have like a 42. We still have like n over 2 here, right? And then that times 42. And then at the same time, how many subproblems we have? 4, right? Make sense? So that's and then about k is equal to 2. That's going to be 2 to the power of 2, 4 to the power of 2, right? And then 42, and then like this. Right, you see the subproblems getting smaller, but at the same time, we have like more problems to solve. Right, so we can do like simple calculation. This is going to be 1 times 42n. This is going to be 2 times 42n. this is going to be like what? Like 2 to the power of 2 times 42n. So see the size of work is going to increase over time, over there. So you can expect what will happen. Eventually, probably that falls into this category, right? Does that make sense? Yeah. So basically, the size of problem is going to be like 2 to the k times 42 n, right? And then if we're plugging this to here, we know the last layer is going to be last. It's going to be what? N times 42n. Make sense? Yeah, because like I divided by 2 here. So it's like if you make sense to you now. So like the number of subproblems is going to increase by 4. You are correct. But the size of subproblem is getting smaller. So if we consider, if we consider like both, and then that's going to be 2, right? So that's the size of work at the final layer. And then if we plug in how many layers we have, if we plug in like log 2 to the log 2n, that's going to be n, right? So eventually we have this. And then you see, like originally, you only have O(n), like linear. And then eventually, the last layer, you have n squared, right? Which means that you actually need to consider the last layer. That dominates the time complexity. So basically the time complexity is going to be big O of 2 to the power of 2. And then if you just plug in the number here, that makes sense as well, right? Because like when b is equal to 4, this is 2, right? And then log 2 is 2, right? So 2 is larger than 1. B is 1. So that's in this case. And then the time complexity is going to be 2 to the power of 2. Questions? No? Okay. Okay, let's look at the other example. That's the first case, right? So first case is going to be like here. And let's see what will happen for the other case. Okay, so how about n squared? Let's consider like each time we're going to solve like this, right? So the time complexity is going to be not that easy, right? N squared. So if you guys want to guess, which case? The first case? Or the second one?
I think it's like,
You take the second one?
Second one is equal.
If they're equal or not? Yeah, okay.
so eventually, the first one went down to big O of n squared, so then if you have n squared at the top, that's what I'm gonna.
Yeah, okay, let's take a look. Okay, so when k is equal to 0, W0 is going to be set, right? And only n squared. When k is equal to 1, what's W1? So you have this square, right? The input size is going to reduce from n to n over 2. So you have this. And then 4 times that. Right? You have this amount. Right? How about like k is equal to 2? You have Make sense? Make sense? So for this one, we know like that's going to be n squared. How about this one? N squared, right? Because 2 to the power of 2 is going to be 4. And then this one, 2 to the power of 2 is 4. 4 to the power of 2 is the same, right? So n squared, n squared. So we have, yeah.
Confused, what's W representing?
Oh, the W means the size of works at each layer.
Okay, just for that individual layer?
Yeah, just for that individual layer. And then eventually we're going to sum up, right? Because we solve this and then that's not done yet. We still need to solve problems. And then for each subproblems, we have layers of problems. So that's going to be like multiple layers until like k is equal to log 2 of n, right? So yeah, we have n squared, n squared, n squared. How about the last layer, like last layer? I use too many space, too much space. That's fine. Last, you just twist a little bit. When k is equal to log 2 of n. That's the last one, right? And that's why it's going to be 4 to log 2 of n, and then make sense? So you can swap, right? So here that's going to be n 4, right? And then that's going to be 2. And this is n canceled out. So eventually you have n to the power of 2. So each layer you have n to the power of 2. What's the time complexity for solving all problems? That's going to be this case, right? Each layer you have n to the power of 2. And then how many layers you have? You have this many. So eventually the time complexity is going to be n squared. Makes sense? So this is what we want, right? Because originally you need to spend probably n squared. But, oh, no. We don't know. Yeah, but this is what we don't want, right? Because the increase over time. I would still need to compare this with the naive algorithm, right? To see if the naive algorithm is more complicated or not. So, okay. That's the 1, 2. So the first case is going to be like this. But I will give you the example of the first case. Right. So the first case. Okay. So let's look at the size of works first as well. Okay. W0. What's the size of works? N squared, right? And then when W is equal to 1, that's going to be 4 times squared, right? So you see, and then how about 2? 4 squared, squared, right? So for this one, that's going to be n squared. And then for this one, that's going to be 4 over 9 n squared. And then for this one, that's going to be 16 over 81 n squared. So you see the size of work is getting smaller over there. Making sense? Yeah. So eventually, let me just erase this part. Eventually, what we have. Hit that? Oh, okay. Yeah. right? And then for W2. Yeah, we can do the calculation about some, but basically the work is going to be, the size of work is going to be right? Because the power of 2 you can put in here, and then that's k, right? K is equal to 1, k is equal to 2. So that's going to be k here. Right, and then you're plugging, what's the last layer? Last layer, k is equal to log 3. Right, plugging log 3 in here. And then what we have, let me just write down here. 4 to the power of k, right? So that's going to be 4 log 3n. The other one is 9 log 3n. Make sense? And then you can do a swap, right? So it's n 4 n 9, and this is n squared cancelled out. You have this term, right? So the last one is going to be n log 3 4. What is this value? Probably roughly around 1.26. So this is smaller than this one. So when you do the summation, as long as they are not infinite, this one is going to dominate the whole complexity, right? So the time complexity is going to be this case. Makes sense? Question? Okay, then still have 2 minutes. I hope I can explain the final problem. So I think one of the question is like a little bit harder. It's this one, right? Right. So we can basically do the same thing for this problem. So for W0, we have n log n. Make sense? For W1, what we have? We have like smaller size that's going to be n over 4 log n over 4, and then 3 times, right? For W2, we have much smaller and then also n log, right? And then what is this one? This also we can express that by something like log n minus log 4. Right? So this like log n minus log 4 to the power of 2. Right? And then the base is 4. So eventually we can express these things by log n minus what? And this is like log n minus 2. So WK is make sense? So what's the last the last one? How many layers we have? Log 0. So k is equal to log n, right? So 0, which means that eventually the size is not going to be reduced to 0. We don't really care about. We only care about the first layer. So even though that you cannot really do the analysis for this n log n. Right? Because like that doesn't really fall into this formulation. But if you know what happened to this formulation behind, you actually can do the same analysis. And then you know that, okay, the size is going to decrease, and then eventually you don't really care. So you just need to care the root. You pay attention on the root. That's it, right? So that's the time complexity. Log n. Make sense? Questions? No. Okay. So which part I can erase? This. Okay, I erase this part, right? This is not really important. Okay, let me explain the first question. The first problem we want to solve. So the first problem is going to be for loop. J is equal to 1, 2, n minus 1, and then we do sorting, right? So the smallest. J, and then for 4, I is equal to j plus 1, 2, n. We do something in the comparison in A is smallest. Then we allocate the new smallest by I, and then swap. So for this, let me give us a little bit here. Okay. So we want to prove the correctness, right? That's the sorting algorithm. We don't know if that's true or not. We want to prove the correctness. And then when you see the for loop, you always can use like a loop invariant, because that makes sure each iteration, the result is what you expected, right? It's like what you expect. So, so we can define the loop variant first, and then check out the whole iteration. Okay, so basically what's the invariant we want to have? That's the array A, right? And then that's the index 1, and that's the index -1, and that's the index j to the n. And right. So the invariant we have is that when we jump into the first step of this loop operation, we make sure that the first j minus elements in this array are the smallest in this array, the smallest. And then also in sorting order. So as we assume when we start solving this, when j is equal to, let's say 2, this is smallest. When j is equal to 3, the first two are smallest. And then also they are in sorting order. Sorting. We assume that. Okay. And then what we can do here is like, oh, we can check out the first step. If the first step satisfies this, and then we can check out if j is equal to k, to j is equal to k plus 1, and then we can check out the termination, right? So we have like 3 steps, like let me just erase this part. So we can check out the initial step. That's going to be j minus 1. What will happen? And then also j minus j is larger than 1, smaller than n. right? Oh, n minus one. It terminates at n minus one. Actually. And then finally, we check out j is equal to n minus one. If that's a result we want, right? So we check out what happened when j is equal to one. So when j is equal to one, all we have zero smallest element. So like 0, not satisfied, right? It means nothing. Okay, so the first case is okay. Okay, so the other case, when j is larger than 1, how about that? So we know this, or if this already holds, what does this mean? This part means like we're finding the smallest from here. Right? Yeah.
So it's like the smallest from a subset.
Yeah, the other part, right? So find the smallest. From here, right? And then what does this mean? Means that we put the smallest to j. Right? So this part means like we find the smallest among these elements, and then this means like we put the smallest in j. So that makes the next iteration qualify for this condition as well, right? Because you say those are already smallest among all of the elements, and then you find the smallest among this part. So we know that that one is going to be larger than those one, right? Because those are already smallest elements. So that one is going to be larger than this one. And then you put that, but at the same time, that element is going to be smallest within this one. And then you put that at j, which means like, okay, the new iteration when j is when n is equal to j or j plus 1, this invariant still holds. Make sense? So that's just the argument you need to write down. Your logic, but basically your logic is here. And then let's check out the final iteration. What will happen? So the final iteration is like j minus 1 is here, right? J minus 1. So when you do the final iteration, you know that from here to here, you already have the smallest among the all array. Right? What's the final one? That one definitely is going to be larger than all of them. Right? So done. The algorithm is correct. Yeah.
What's the sorting? What's the name that's over
I actually don't know. It's not a good solution.
Yeah.
N squared. So what? No, it's not bubble solve. It's not. I think it's not bubble solve.
It's selection.
Selection?
Yeah.
No.
Like, you select the smallest, like place it first. It's
No. Selection sort. I think the complexity is going to be n log n as well, because you have the pivot, and then you can randomize that. But you will learn that later. I don't think
like a variant.
yeah, you will learn that later. Yeah. But basically we just want to prove the correctness. And then for the algorithm you learn, you still can use this loop invariant. Yeah.